Now, the second rule of temperatures, and that's the only other thing about temperature we've got to say, okay? The second rule of temperatures is also something you may have experienced. Imagine a piece of coal. If I just have a piece of coal sitting here at room temperature, what color is coal most of the time? If I have a piece of coal sitting here at room temperature, what color is it? Black, right? It's black. And would I hurt my eyes looking at that piece of coal? Would it be dangerous? No, right? And that's actually according to rule number 1. Temperature rule number 1 said that if this guy's cold, he's not going to give off very much light. He's going to be dim, right? So a piece of coal looks black and dim because it is cold most of the time. But if I heat up this piece of coal, it would eventually start to glow, because according to rule number 1, if I make it hotter, it's going to get brighter, right? But it doesn't just get brighter as it gets hotter, like rule number 1 said. Something else also changes as it gets hotter. Does anybody know what else changes about this piece of coal as it gets hotter, other than the brightness? The color changes, right? The color changes. That is correct. So the color changes as it gets hotter. And the second rule of temperatures is telling us that the color it looks will tell us something about the temperature, okay? So yeah, you guys, the other things you guys are saying are things that do change. But I was looking for that specific one. So here we go. Let's think about the colors of coal. Let's say I've heated it up and it is just barely hot enough to glow in visible light. What color does it glow at first? As you just have barely made it hot enough to glow with visible light. What color is it going to be when it just starts to glow? And if you haven't ever been to a cookout, then this might not be something you're familiar with. When it just barely starts to grow, it'll actually be red. Okay? It'll be, like, if I'm talking just barely, it's red. And the other colors you guys mentioned are close. They're close. Because if you heat up that piece of coal, it'll turn red. And if you make it a little bit hotter, it'll turn orange. And if you make it a little bit hotter, it'll turn yellow. But red is when it's just barely hot enough to glow. Orange is a little bit hotter. Yellow is a little bit hotter than that. And if we make it really, 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 really hot, what color will that coal glow? Oh, somebody got it. Eventually, it turns sort of like a bluish-white color, right? A bluish-white color. Yeah, a bluish-white color. So let's think about this. There's a pattern there, okay? As it got hotter, the color we saw turned from red to orange to yellow and eventually on towards blue. What are we basically moving through? What's that order of colors we're seeing right there? Some of them might be a little missing, but what order are we going through? Red, orange, yellow, eventually blue. Yeah. We're going through the rainbow. That's correct. We're going right through the rainbow. And let's see if we can put this together. How is the rainbow organized? The rainbow, we said, was organized according to a property of light. Which property of light? It's organized according to... Remember, what are the different colors? Okay, they are all visible light. That's good. That's good. But how is the visible light organized? It's organized according to wavelength, right? Remember, we said that the reason the rainbow is in that order is because it starts with red at the long wavelength side, and then orange is a little bit shorter, and yellow is a little bit shorter, and blue is even shorter, right? So, here we go. That color that we see is going from red to blue. So what's happening to the wavelength of the color we see as the coal gets hotter? As the coal gets hotter, it goes from red to blue. So is the color we're seeing getting longer or shorter? It's becoming shorter. Remember, red is the longest color, blue is the shortest color. So it gets shorter and shorter and shorter and shorter. So that is actually the second rule of temperature. It's using the color to figure out the temperature of the object. And let me, I wrote it out ahead of time again. Of course, it's going to freeze on me. So here we go. Temperature rule number 2 is... Remember, this is just a fancy way to talk about the color change here. The higher the temperature of the object, the shorter its peak wavelength. The higher the temperature of the object, the shorter its peak wavelength. Let me make that make more common sense. Okay, let me get my graph back in here. Okay, now, 2 things. Remember, let's make sure we understand the language here. Peak wavelength is just whichever wavelength that object is giving off more than any other one. So this right here, that right there, that's the peak wavelength of this object, okay? And the peak wavelength is the wavelength you're going to mainly see when you look at that object. So, for example, when we've heated up the piece of coal until it glows yellow, that doesn't mean it's only giving off yellow. It just means that it's giving off more yellow than any other color. So we see yellow, right? And so if we made a graph of that, the yellow piece of coal would still be giving off most of the other wavelengths, but it would have yellow right here, okay? And what we're saying here is that where that peak is shorter the hotter the object is. So instead, again, if we got it hotter, that peak, instead of being at yellow, would be at blue, okay? Now, we got to be careful here. What is that going to look like on the graph? I do not mean by saying shorter here that the graph will get shorter. If the object gets hotter, this graph can't get shorter in intensity, because rule number 1, remember, said that if this thing gets hotter, the peak gets taller, okay? So that's not what I mean. It says the peak will happen at a shorter wavelength, and wavelength is the left and right part of this graph. So what I'm saying here is that if this thing gets hotter, it's going to move horizontally. And let's see if we can put this together. If we get this object hotter, that means its peak wavelength will be shorter horizontally. So will this graph go left or right if this object gets hotter? Let's take give me at least a guess on this. If we need that peak to happen at a shorter wavelength, are the shorter wavelengths towards this side, or are they towards this side? So remember, wavelength increases as we go to the right. So the longer wavelengths like radio are over here, And remember, gamma rays, the shortest wavelengths are on this side. So what that means is that if this peak happens at a shorter wavelength when it gets hotter, the peak would have to move towards the short end. So according to rule number 2, this peak would actually move left. Okay? So don't worry if you got that wrong. We haven't done a lot of graph reading yet, so it's okay. So again, the two rules, number 1 says that the hotter object will be brighter, so the graph will go up. And rule number 2 says that the color will change in the blue direction. It'll go from red towards blue, which in this case is moving to the left. So the graph will get taller and move to the left if the object gets hotter. And the way that this is useful is that we have tested objects of a whole bunch of different temperatures. So we know how high and how far to the left every temperature is. So when we look at a mystery object in space and take its spectrum, we can just match up its height and how far to the left it is to all of our known temperatures to figure out the mystery temperature of the mystery object. One last couple of questions I got right here before we move on to the last thing that we can learn from the spectrum. Let me show you a picture from the book. Here we go. And on this picture, don't worry about any of these words. Don't worry about reading any of this. I just want this graph down here. So down here we got, this is the same kind of graph that I'm showing. Don't freak out, it looks way more complicated. But we got wavelength down here. We've got intensity over here. And what they've done is they've got 1, 2, 3, 4 different objects graphed on the same graph. And even if they didn't tell us the temperatures over here, let me see if I could sort of, I'm blocking these temperatures. Can you tell which one of these objects over here is brightest? Or sorry, is hottest? Which one of these objects is hottest? Is it this one, or this one, or this one? Let's say A, B, C, or D. Which one of these is the hottest? A. A is the hottest, right? We know it's hottest because it is the tallest, right? That means it's the most intense, it's the brightest. And you'll see the peak here is the farthest to the left. So both of those say that that one's the hottest. Does that make sense? So, don't worry too much about being able to read graphs like this. Like, don't worry about having to pull numbers off them. But if I did give you a graph like this on the test, you should be able to tell me which one of them is the hottest according to those temperature rules. And again, you're always looking for the one that is the tallest and the farthest to the left to be the hottest one, okay? And what they've graphed here, these are 3 different stars, right? 3 different stars. And down here we have humans. Why is the human graph so short and way over on the right? Why is the human graph way down here? What's true about humans, probably, compared to these stars? Yeah, we're too cold, right? We're not as hot as those stars. And in fact, see how our peak is not even in the visible? A human being doesn't glow with their own visible light, right? Stars do because they've got a lot of intensity in the visible part. We don't. So our main type of light, right now you're glowing. You're just glowing in a wavelength that humans can't see. right? What wavelength do we glow at? Well, we glow at roughly this wavelength, which is in the infrared. So humans glow in infrared light. That's why if you get yourself some infrared goggles, which are a type of camera that can see infrared light, you can see a human being even in a dark room because we are like infrared light bulbs. Also, how could you figure out that a human being was giving off infrared light even if you didn't have infrared goggles? Yeah, when you feel body heat coming off of someone, you're detecting their infrared light, right? So remember, we said that our bodies can detect infrared with your skin. So yeah, that's the infrared light. If you could see that, everybody would look all glowy, right? Okay, that's temperature. We're done with it.